All right, thanks everyone for being back on time. We are going to continue with Alex Lau, who is an assistant professor of computer science here at Yale.
Great. Thank you, Ilker. Thank you so much for everything you've done to organize the workshop, and thanks everyone for being here. So as Ilker mentioned, I'm in the computer science department, and the sort of starting point for the jumping off point for a lot of the work that I do is the observation that over the past few decades, the sort of tasks that we ask our computers to perform have become more and more probabilistic in nature. So, if you go back to the 1980s, it was mostly the case that what we wanted our computers to do were solve logically well-specified problems. Find the answer to this database query, for which there is a correct answer, and you can design algorithms that compute that correct answer. And there are some exceptions to this, like the earliest numerical weather prediction algorithms and the Kalman filters used in space missions. But it really wasn't until a bit later, so the early 2000s, when I was learning to program, that we started to ask our computers to do things that looked a little bit more like drawing inferences and making predictions, right? Inferring which websites were trustworthy based on who else linked to them in the web, or predicting what movies you were likely to want to watch based on your viewing history, but also everyone else's viewing history on Netflix. And in the last 10 years or so, the scale and complexity of these inference and prediction tasks has really exploded, right? We're trying to build AI doctors that infer your diagnoses from your symptoms and predict treatments that are likely to help you. We're trying to build autonomous cars that can infer the geometry of their environments and predict how pedestrians are likely to move, right? And you might expect that given this big shift in the kinds of tasks that we are asking our computers to solve, that we'd see a corresponding shift in the sort of software engineering methodology in the stack that we use to build them. And to some extent we have. So we've seen the rise of these tensor computation frameworks like PyTorch and JAX that do a lot of things that make modern machine learning work the way it does, right? They compile code to really fast implementations on GPUs. They automate the derivatives that we need for gradient-based learning. But in some sense, these tools are still surprisingly low level. What I mean by that is that the tasks that we're building systems to solve are probabilistic in nature. If you go and look at sort of the papers that introduce the algorithms that we use to solve them, they're full of probability theory. But then if you actually go look at the code, you'd be hard-pressed to find those probability distributions. Sorry, I think that there's some auto advancing on. I might just click use timings off and start again. Okay. Thanks. Sorry about that. Right. If you go and look at the code that people are writing, it's hard to find that probabilistic thinking. Really, that probabilistic thinking has happened on pen and paper, in the internal documentation of the companies building these systems, in the papers that people have written. And then the results of all of that thinking are that you have some algorithm that you go and implement. And so, by contrast, in my lab's work and my collaborators' work, we think about sort of a new class of programming languages and tools, probabilistic programming languages, that treat probability distributions as first-class citizens and give you sort of first-class ways of working with them. And probabilistic programming is a really broad field, and these various languages differ in their goals. Some of them are aimed more at specialized kinds of probabilistic computations, like the kind you might have to do for data analysis as a social scientist. But I'm going to focus in this talk on several open source systems that my collaborators and I have been building over the past few years. And in particular, on three places where this sort of probabilistic programming perspective has shifted at least how I think about efficiency in AI systems, right, the topic of this workshop. So I want to offer sort of three little vignettes or case studies that might hold lessons for how we think about efficiency in AI, given the kind of new way that we could build probabilistic software with these new tools. And the first of these vignettes is about probabilistic inference. So let me start by giving you an example of a very simple task that people seem to solve more efficiently than AI. So in this plot, I've secretly imagined a curve, and I've placed several blue dots close to the curve, and I've also added some distractor blue dots away from the curve. And your job is to look at the plot and try to figure out what the curve is and which dots are the distractors. And if you look at it just for a couple seconds, you'll probably see a curve jump out. At least when I've asked a couple friends just to sanity check that I wasn't the only one, they saw this curve, right? And then a couple dots at the top. Okay. Now, how should we model this capability that people have to do this in a couple seconds computationally? And one idea with a long history in computational cognitive science is that you're doing sort of rational Bayesian inference in a probabilistic program that models this scenario. I think a lot of people here are familiar with probabilistic programs. We've heard a little bit about them already today, but let me just recap so that we're all on the same page. When we write a program that makes random choices during its execution, we are implicitly defining a probability distribution on all the possible outputs of the program, given its input. So for example, this program here is a little Python program that takes in a number theta as input, flips a coin with probability theta of heads, then uses an if statement to decide whether to return 0 or theta over 2. And we can think of that as a procedure that we run, or we can think of it as implicitly and unambiguously defining a probability distribution, p of x given theta, right? That says the probability that x equals theta, that x equals 0 is theta, the probability of x is 1 minus theta if x is theta over 2, and all other outcomes are given probability 0, right? So these are just two different representations of the same mathematical object. And if our programming language is sufficiently expressive, then we can write down lots of interesting probability distributions in this way, including all the sort of classes of well-studied distributions for machine learning and stats literatures. In fact, if our programming language is expressive enough, we can represent any computable probability distribution. In particular, for example, we could use loops and if statements to write down a program that models this curve detection scenario. So here's a program that encodes a generative model of how this plot came to be. Basically, I'm just translating the assumptions that I told you about how I generated the plot into code. So you might model me as choosing a random polynomial with a random degree and random coefficients, and then choosing some proportion of the points to make outliers and or distractors, and then looping through all the points, flipping a coin for each x coordinate to decide, do I want to make that a distractor or not? If it is a distractor, I just generate it from some broad distribution. If it's not a distractor, I generate a blue point that's near the curve that I picked. And then I return to you this curve, the list of distractors, and the x's, y's pair. So when I write this program, I've implicitly defined a probability distribution, a joint probability distribution, over what curve, the latent curve that you don't see, the latent set of distractor items that you don't know, and the actual data that you observe. And the hypothesis is that if we have this kind of representation in our head, then maybe we can run some kind of inference algorithm in order to condition this probability distribution on the data that we saw. And this is sort of this posterior distribution over curves and distractors feels like what we are computing when we see the curve and identify the distractors. But it's one thing to write down P of F distractors given data, and it's another thing to compute it. And a commonly levied critique of probabilistic programs is that although they are a very expressive representation for models, this expressiveness comes at a cost, right? And so the critique basically goes, as you know, Charles Sutton, who's was one of the people behind one factor graph representation for probabilistic models and is now an engineer, a research scientist at Google, put it, it's like inference becomes very challenging, particularly because, or precisely because the framework is so general. So the idea is that like knowledge representations maybe live on this spectrum, where at one end of the spectrum you have like very restricted knowledge representations that can represent a small class of probabilistic models, but the benefit is that you can use those restrictions and exploit those restrictions in order to do really efficient inference. And as we get slightly more expressive to, you know, Bayes nets with finite discrete variables or something like that, we can represent more things, but it becomes a bit harder to do inference. And probabilistic programs are maximally expressive. We can put any computable probability distribution there, which means that like the inference algorithms that we can apply must be like kind of very generic and, you know, not really very efficient. And indeed, if you look at what the standard sort of, you know, if you open up the probabilistic programming language web people and run its inference algorithms, and you look at what they do on this model, it's not very encouraging. So here's the data that we were looking at. And if I run importance sampling, so here's one algorithm that you can run, it just simulates, I'm simulating here 15 million runs of the program that I'm showing in yellow. And what you're seeing in blue are the highest scoring runs so far, where the score of a simulation is based on sort of how plausible the data is given the simulated parameters that we drew. And you can see that even after 15 million simulations, taking way longer than any of us took to identify the right answer, we don't have the answer that we all identified, right? And you might think that this is kind of implausible because surely, this isn't that big a space. Surely we must have drawn that downward curve in 15 million simulations. But you have to remember that a simulation of the program doesn't just include the curve, it also includes the choices of which things are distractors and not. So if we happened to randomly choose certain things to be distractors that were not the true distractors, then this curve would look very bad because it wouldn't explain the distractor points, right? And so the chances of getting everything right are small. And there are better algorithms than importance sampling. So for example, I can run Metropolis Hastings, which iteratively refines a hypothesis. But this also has failure modes. It can get stuck in a mode, a local mode. So here we're seeing that it's still not finding the solution that we found, even though it is an actual better solution under the model. OK. So, if our answer to how do humans efficiently find the curve is Bayesian inference, our explanation is at least missing a step, which is how do you make that Bayesian inference efficient? And this is sort of an even, this is a different objection from the one that Tyler covered in his talk this morning, which is how do you even get this probabilistic program that's small enough to do inference in the first place? This is a pretty small probabilistic program. This is a probabilistic program that is pretty minimal for representing the task at hand. It's already gotten rid of all of the stuff about the world that's not relevant. And yet still, it seems difficult to do inference. And there are answers that have been proposed to this. So for example, one idea is amortized inference, which says, well, those guesses I was making were pretty dumb. Surely I've learned to make better guesses about what the curve is based on the data. And in fact, one way I could learn to make those better guesses is that I take the probabilistic program, I generate lots and lots of samples, and I can train a little neural net based on those full samples to go from the observed data to the latent variables, because my full samples are like labeled supervised training data, right? But if you think about how fast you were able to make this inference, it doesn't, if you were quickly training a recognition network in that time, based on sampling this probabilistic program, that training must have happened very fast. Another idea is that, well, maybe we're actually constantly amortizing inference in general. So we have this sort of like big recognition network that actually can be conditioned on what probabilistic model we're doing inference in. And this has been, people have tried to realize this. So like Mike Wu and Noah Goodman have a paper called Foundation Posteriors, where they try to train a transformer across lots and lots of probabilistic programs to do inference. You could also maybe just argue that our modern reasoning models, our modern LMs, or even without the reasoning, just our modern LMs are a form of this, right? Because every prompt that we give them is kind of a new reasoning scenario, and we train it on huge amounts of data. But it's interesting that for this task, at least, if we ask our best LMs, they're not great at it, right? Even this very simple task. And we can kind of think about, different ways of instantiating this amortized inference hypothesis. One is that the right computational models to use are kind of small models like Haiku that are not reasoning models that can just look at this data set and give me an answer. So it's true that Haiku completes in about 7 seconds and gives me an answer, but it's the wrong answer. It's identified the wrong outliers. They don't really make sense as outliers. We could also say, well, we should be using these sort of reasoning models, but these take 2.5 minutes, and they're doing a lot of things like writing Python code to try fitting all these different curves to different subsets of the data and so on. And so, we can argue about how plausible that is as a model of what people are doing, but one thing that it doesn't have is speed, right? It takes 2.5 minutes, in which time humans could solve this task 100 times over. So what is going on? And I should say Opus does eventually get it right at the end of those 2.5 minutes. OK, so what's going on here? How do we solve this puzzle? And I'll argue that the key is to recognize that this trade-off that we were painting before between expressiveness and tractability is not quite right. It's only half right, because it's true that programs are a very expressive and general representation, but they're also a very rich representation. There's a lot of structure present in a program that's not present, actually, in something like a discrete Bayes net, right? In fact, discrete Bayes nets can kind of be viewed as like coarse dependency graphs, which sometimes compilers and other program analysis tools create as a coarsening of the semantics of a program. But the program itself has a lot more information than that. And so one hypothesis is that people flexibly exploit whatever structure can be detected in a probabilistic program to make inference more efficient. And that means that even though in the worst case it's still true that there are going to be probabilistic programs that are totally intractable to do inference in many cases it may be possible to do inference quite efficiently, and maybe even more efficiently than we would be able to do with a different representation of the same model, right? And so with Maddie Bowers at MIT and my student Theo Long here at Yale, we've been building an inference engine for probabilistic programs that tries to exploit program structure in this way. The language is called Pluck. And on our example program, I can run Pluck's inference, and within a second, I get an exact posterior here. So I'm showing 50 samples from the exact posterior, but it is computing the exact posterior behind the scenes. And this is not just a tool for this model. We have sort of, we can run Pluck programs that do things like clustering or analyzing sort of a susceptible infected recovered model, or generating binary search trees that are balanced and valid binary search trees by conditioning on a just generative model of trees and stuff like that. And it's all the same system that's doing this. So I'm not going to go into a ton of detail on how Pluck works, due to time constraints. But it's basically using a combination of existing and new techniques from the programming languages community to exploit structure in a probabilistic program. We're kind of throwing at least part of the book on how you do program analysis at the problem of probabilistic inference, right? And so there's this idea called lazy symbolic execution, where lazy means that we try to avoid executing any part of the probabilistic program that's not actually directly relevant to the query. And symbolic execution means that we're symbolically exploring those paths that are relevant to the query. This gives us a new representation of, here's our observation as a formula. We compile that to something called a binary decision diagram and continue to do more analyses on this. So there's a bunch of different representations here that are being derived from the probabilistic program. But the upshot is that in many models, Pluck can exploit enough structure to do really efficient inference. It can exploit independence relationships. It can exploit conjugacy of continuous variables. And Pluck is not perfect, and I suspect that there's many more avenues to explore for exploiting more structure in a broader class of programs. And I also want to be clear that Pluck doesn't magically make inference tractable. These are all models that don't have other a priori arguments for why inference should be intractable. These are models where, actually there is some reason that the model is tractable, and the key is figuring out what that reason is and exploiting it, right? But I think it's sort of a little existence proof, and there's a bunch of other very recent works in the programming languages community that are also exploring new ideas about how to apply PL techniques for inference in probabilistic programs. I think it's kind of an existence proof that this efficiency versus, or tractability versus expressiveness trade-off isn't quite the right picture to have in mind, right? Now, this still leaves us with this question, of course, of how do we get these small probabilistic programs that are tractable somehow to do inference in? And Tyler presented one answer for that today. I just actually took Haiku here and asked it to please generate a probabilistic model of this scenario. And within 7 seconds, at the same amount of time that it took to try to incorrectly solve the problem, it did just spit out with no, you saw the whole prompt, it was that long. Like, it spit out pseudocode for a generative model that's basically exactly the generative model that we used for the scenario, right? So I think there is promise that that these tools could help us get to a point where we have these small models that we can do tractable inference in. But another source of small tractable inference problems is that they arise as subproblems of large intractable inference problems. So this was, once we have good ways of doing small tractable inference, we can try to solve large intractable inference problems by calling out to it. So this is a project I did with a collaborator, Monica Agrawal, who's now an assistant professor at Duke. And we were trying to figure out how to get computers to reason probabilistically about relational data, right? So there's a lot of domains where we have data sets that are kind of flat, like a data set of citations, right? But we as people, when we read these data sets, we know that there's rich relational structure. There are things in the world, and they're related to each other, and we're just seeing some like corrupted join of that database. And people navigate this very flexibly. So for example, if I'm looking at this data set of apartment listings and I'm trying to figure out what state that missing null value is, I can sort of go through a pretty complex reasoning process to think it through. For example, the first thing I might notice is that the city Beverly Hills is not one I've heard of before, but I've heard of Beverly Hills. I think maybe it's a typo, and I look at the description, and I see that in the description it's spelled Beverly Hills, so okay, I think that we're in Beverly Hills. But also the price is $1,000 for a 2-bedroom apartment, which doesn't feel right for Beverly Hills. So that's getting me confused. And I might search the database for other apartments that this couple have listed. And I might find, for example, that Tim and Sarha Jones, which is a slightly different name, but I already think these people make typos. So maybe it's the same people, have listed apartments for similar prices in Missouri. That's weird. Why is someone listing apartments in Missouri and in California? And then I might, go to the internet or just search the rest of the data set, and I might see that there actually is a Beverly Hills in Missouri. And even though I couldn't be certain, if I had to place a bet, I might choose Beverly Hills, Missouri, as the way to complete this row. So how could we make a computer do this kind of reasoning? The system that we built is called pclean, and it works like this. It takes in a flat data set as input. Here I'm showing 4 rows out of 2 million from a Medicare data set of physicians in the United States and where they work. And I also give in a probabilistic program, which is generally around 50 lines of code in our examples, that basically expresses an ontology that we expect to be underlying this flat data set. So what is the schema of the relational database that we think underlies this? Well, we think physicians go to schools and they work at medical practices that are located in cities. And pclean's inference algorithm tries to infer then the contents and the structure, or and which objects exist in this latent relational database based on the observed data. So it's trying to find what database, if I made it dirty and then flattened it, would give me my original data. And once you have this latent database, if you can get it, you can sort of redo the join and get a reconstructed clean data set. So we found, on this Medicare example, there were 8,000 changed cells, and we ordered pizza and went through and Googled and tried to figure out if those 8,000 changes were real fixes to real errors, and we were able to verify that 96% of them were. There were also 1.5 million imputations, which we did not go through manually, but in a sample of 100 of them, we found that 90 we could find a LinkedIn page or something that justified the imputation. And how pclean works behind the scenes is, it's this huge probabilistic model that has uncertainty about this whole relational database. But we're using an algorithm that goes sort of row by row. So what you're seeing here is that the rows of the flat data table are streaming in on the left. And for each row, the problem of how do I explain this row, given my current hypothesis of a latent relational database, is small enough that we can use tractable exact inference to solve it. Okay? So each new row that's coming in, we're asking, is that hospital the same hospital I've seen before, or should I think that it's a new one? And if it is a new one, what should it be called, and where should it be, based on the entries in this row? And this algorithm is kind of append only, so sometimes it will make short-sighted decisions based on a row that's misreporting data. And so there's also a step of Bloch-Gibbs rejuvenation where it will go through all the objects in the latent database, which I'm highlighting in yellow, look at all of the other objects in the database and the data, which I'm highlighting in blue, that are currently hypothesized to be reflecting information about that object. And in light of all of that, pose the tractable inference problem. How should I repropose these yellow highlighted values? Okay, so that was vignette 1. And I think, the other 2 vignettes are shorter. So I think I should be OK on time. But the takeaway from that is that, our maybe cached ideas about what's tractable and intractable, the idea that like, oh, ideal Bayesian inference is this intractable thing that we approximate with amortization, maybe we should revisit and think actually that sometimes doing ideal Bayesian inference where it's tractable could actually make our amortized models more efficient. Right? Okay. Vignette 2 is not about inference, it's about learning. So a lot of learning these days happens via gradient descent, right, which is a very simple algorithm, 3 lines of code, where we say, while we haven't found the right parameters of our model, we look at the gradient of the loss. So in what direction does the loss decrease the steepest? We take a step in that direction, and then we go again. And although this is a very simple algorithm, it's worth noting that if you go back to like early papers, like Schmidhuber's LSTM papers, there are pages and pages of derivations just to figure out like what the gradient is. The math of computing the gradient had to be done by hand, and it was tedious and required some amount of expertise. And at the end of all these pages, you'd see, well, in order to implement the backward pass for backprop, all we need to do is implement equations, 19, 20, 21, 22, 23, and so on, right? This is no longer the experience of using gradient descent for the most part because of an innovation called autodiff, which is an algorithm that takes in a loss function represented as a program and produces a new program that is guaranteed to represent or encode the derivative of the function encoded by the original program. This means that in order to implement gradient descent these days, it really is just 3 lines of code. And this sort of change in how machine learning models were implemented has led to a huge explosion of exploration in the space of models that we try to learn by gradient descent. I think a lot of the time the AlexNet moment is credited with resurging interest in deep learning, which I think is basically right. But that interest couldn't be converted into research activity until you had autodiff, right, widely available. Now, we're in an interesting moment now because a lot of the optimization problems that we're trying to solve, it turns out autodiff doesn't actually apply to. So we're a little bit back in the world of having to do math by hand. So what do I mean by that? Well, a lot of the time, what we want to do is optimize an integral, an expected value, over some probabilistic process. So for example, you might think that we're trying to optimize the parameters of a robot arm, and we have some simulator that's stochastically able to simulate sort of the grasp error of the robot arm when its policy has certain parameters. And we're able to return that. But what we want to do is optimize or minimize the expected grasp error, right? The average grasp error across simulations. And unfortunately, autodiff doesn't let us, in a neat way, do that. So there are these tasks also show up when we're training language models. We often want to sort of, like in RLHF, we want to optimize the expected value of the process, the stochastic procedure that samples a completion from a language model and then feeds it to some reward model, right? And although this is really easy to write down as an objective, there is no button, no autodiff button we can push. Instead, you wind up with papers like Secrets of RLHF and Large Language Models, Part 1. And so there's something, I think, interesting here about this picture, because what are these secrets doing? Well, they're coming up with some way to estimate this gradient based on some simulations. And I think we're used to thinking of gradient descent maybe as this very data-hungry method, right? Very inefficient in terms of the data that it uses. But in some sense, like, there is no data in this picture, right? When we actually run the reinforcement learning from algorithms, the data are the rollouts of the RL algorithm. But the fact that we need so many rollouts is actually more about the inefficiency or the high variance of our gradient estimator than it is anything about gradient descent as an algorithm itself. And so, and in fact, many people are not even, I think a lot of people are using unnecessarily inefficient gradient estimators. A lot of people are using estimators that aren't even unbiased, right, that are actually wrong. There was a paper earlier this year. Now that we've back to having to do all the math by hand, a lot of people are doing the math wrong. This paper is called A Comedy of Estimators. And it was pointing out how the recent literature on RL for language models is riddled with math errors, basically, about how to derive these gradients. So I won't go too much in detail about this, but we've been working on a sort of new autodiff algorithm for differentiating expected values. And one of the things that this autodiff algorithm lets you do is annotate your program in certain ways in order to change how much effort it spends trying to estimate the gradient versus how accurate that effort is going to be. And we found that if we go and revisit certain sort of papers that were training, that were optimizing expected values by gradient descent, and we revisit them, and we do a sweep through all of the different gradient estimation strategies that our autodiff system can handle, we find that the best strategies outperform the worst strategies by an order of magnitude, and the worst strategies are the ones that people were using in the paper, right? So there's a lot of room on the table here. And also, if you then go look at what these strategies are, oh, I'm missing that slide. But if you go and look at what these strategies are, they're often somewhat cognitively interesting. So I think an interesting thing to, like it's about how do you efficiently get an estimate of how to update your parameters on the basis of not that many rollouts, for example. And so I think this is sort of a place where we could stand to do more thinking about how to efficiently estimate gradients. And we're trying to build sort of the programming frameworks. There's a recent paper that's coming out this summer in PLDI with a student, Gaurav Arya, and Farasad at CMU, where we're sort of presenting a programmable framework for gradient estimators. And a lot of the gradient estimators that you get as you sort of vary the parameters are ones that people already know, but there are also some new ones that turn out to be lower variance than the best ones that we know. Okay, I'll just quickly end with the third vignette, which is about efficient reasoning with language models. So language models induce distributions on strings. So if we tell a language model to tell me a joke, right, that prompt induces some big distribution on all the jokes that the language model could give us. And what we actually see in our ChatGPT interface is just one sample from this distribution. And because natural language is so expressive, we can express, we can sort of modify what the language model is giving us by modifying our prompt in really generative ways. So I can say, tell me a joke about animals. And intuitively, what I want to happen is for it to upweight the jokes about animals, downweight the jokes that aren't about animals, so that when I sample, I'm really likely to get a joke about animals. I could also even ask it for weirder things, like tell me a joke that only has short words in it, less than or equal to 5 letters. And I would hope that most of the jokes would be downweighted, but then the few that it knows that happen to have less than or equal to 5 letters in it would be upweighted, and I'd get to hear about a bear with no teeth, which is called a gummy bear. Okay, so this is how we hope that it works, but we all know from using these models that prompting alone can be unreliable. So when I actually asked, this was GPT 4.0 at the time, I think, tell me a joke about animals, sometimes I got answers like, why don't scientists trust atoms? Because they make up everything. Oh, wait, that's not an animal joke. Here's one, right? When I asked, tell me a joke with only short words, I get something like, why did the cat sit on the mat? It saw a hat, which actually does satisfy the constraint, except that it's not a joke, or at least not a good joke, right? And it also does give some jokes that don't satisfy the constraint, like why did the ant get sick? It caught a bug, right? But caught is not 5 letters or less. Now, one answer to this problem that prompting is an imperfect mechanism of control is scale, right? We just make the models bigger, we train them harder, and they get better and better, and we notice this less and less. But as our third sort of thing to think about in terms of efficiency, I want to ask, like, is that the right answer to this problem? And so probabilistic programming gives us an alternative that says, look, these models, these language models, they are probabilistic programs. They're programs that generate random things. And they're really good probabilistic models of some things, right? They are not general purpose oracles. But maybe we can embed them in bigger probabilistic models and use them as what they're good for, models of language, and not rely on them to be full oracles. So for example, here's and this is the last example that I'll show, but here's a little fun task that comes from the Sparks of AGI paper that was released by Microsoft right when GPT-4 came out, which is to generate the first line of a poem that if I read the words in reverse order, could plausibly be the last line of that same poem. This is a kind of difficult task, and it's one that GPT-4 struggles at. dawn silence whispers softly, evening's echo fades. You can try to read that backward. It doesn't make any sense. I asked GPT 5.5 last night, and it gave me a huge list and then told me its favorite one. And really, most of these are really bad, but its favorite is also bad. Wings has grief even morning before is what you get when you, when you reverse it, right? But we can actually take a quite small language model and do this. We can say, look, there's some distribution that we get when we say the poem begins with the words. We get some distribution over completions. We get some other distribution when we say the poem ends with the words, right? And we can take the push forward of this distribution by the reverse function, which just means reverse every string here, but keep its probability the same. I get a new distribution, right? So every string here is some good completion of this one, but reversed. And then I can take these two distributions and multiply them so that only the things that are high probability strings under both of these distributions are upweighted. And then I can run a sampling algorithm from my probabilistic programming language in order to try to sample that distribution. And I get things even using a very small language model, like cold and dark was it when winter last, which reverses to last winter when it was dark and cold. Or there was nothing but love in her eyes her in love, but nothing was there, right? And so this is showing that like a task that's really difficult to achieve just by scale, maybe we can achieve by adding sort of a layer of rationality on top that says, here's what the task is, here's how you should use your knowledge, which is one of the things that's really impressive about LMs, in order to help solve the task, but here's the structure on the outside. And we've applied this to more real-world tasks as well and shown that you can sort of make small models perform as well as large models by adding this kind of exoskeleton on the outside. And we've also, these are with handwritten probabilistic programs, but we've also tried asking the models themselves, kind of in the spirit of the model synthesis architecture work, to, from a natural language prompt, figure out what probabilistic program to write that controls a fleet of smaller language models who are going to go off and try to solve the task via sampling. And we've shown that that can make that fleet of smaller models outperform the smaller model, outperform the larger model, and get up to, at this point, this was right when O1 had been released, and get near the performance of O1 on the data set of tasks that we were looking at. Okay, so I'll stop there. Sorry, I know I only have a couple minutes for questions, but thanks, everyone.